Hello, I'm Hadas. I'm very excited to be talking to you here today. I'm here to talk to you how we migrated a mission-critical service to Go. This service is very special to me and to all of us at AppsFlyer, since it is the first service we had in Go. You'll have to wait until the end of the talk to know if the experiment was successful and just how many services we now have written in Go. You'll walk out of here with the tools to migrate a mission-critical service and maybe some courage to introduce a new language. So I am Hadas. I'm a software team lead. I'm a proud Gopher. I love Go, I love Clojure, and distributed real-time systems are really the sort of thing that gets me excited. And how can we do without? A little bit about AppsFlyer. AppsFlyer is the world's leading mobile attribution and marketing analytics platform, helping app marketers make better decisions every day. And what is mobile attribution exactly? Very simply, it's the match between a click on a campaign or a view of a campaign and an app install. This really means that whenever you click or view a campaign or do a meaningful event in an app that's installed on your mobile, we receive an event. From that, we can derive how campaigns are doing and if they're worthwhile at all. There are many additional features on top of it, but enough marketing materials for now. We have over 250 engineers worldwide, 200 unique microservices, thousands of servers up on AWS, 90 billion events coming into our system a day. And I'll say that again because that's a really big scale. 90 billion events coming into our system a day. We have 85,000 apps which have our SDK implemented, and our services are built using a microservice architecture, and we have tens of deployments a day. About our culture. We believe in simplicity. We're Clojure first. We're actually one of the biggest Clojure shops in EMEA. We like to experiment, and we're not afraid to rewrite, change, and start over to fit our code to our ever-changing needs. Now that you learned about AppsFlyer and how we're a 24/7 SaaS company, serving end users from all over the world, all day, every day, you can probably understand why we needed a seamless and zero downtime migration. Now let's go back to the reason why we're all here, how we migrate a mission-critical service to Go. There are 5 steps we followed in order for this project to be successful. We identified the problems, we defined our goals, we chose the right technology for us, we designed the new service, and we had a full company migration. Each of these steps will be carefully detailed over the next half an hour or so. So a little bit of context. API Gateway is the service we eventually migrated. An API Gateway is a reverse proxy which exposes microservices as APIs. As the name implies, it acts as a gatekeeper between clients and microservices and serves as a single point of entry to a system. It reduces code complexity by having a single, central, and manageable way to enforce access and to impose limits. Typical features of an API gateway might include authentication of a request, authorization, security policy enforcement, and throttling requests if necessary. Now, let's dive into our implementation of our old API gateway, and feel free to try and guess what issues we had and why we needed a new solution. So, our first API gateway was also called the bouncer. It performed authentication, authorization, and reverse proxy. It served as a single point of entry to the AppsFlyer management system, serving over 80 API services and around 35,000 customer accounts. It was written in Clojure, the language all AppsFlyer engineers felt the most comfortable with at the time. Now let's dive into the architecture. The bouncer would have requests coming in from the web. It would then authenticate each request out of an account repository. The bouncer would then dive into authorization. It would authorize using a blocked set of URLs, which were registered by each microservice, to an outside database, which you can see here is the console. Before proxying the request on, the bouncer would add all user and account data to the header of the request. And then the bouncer would proxy the request on to a set of exposed microservice and routes, also exposed by each microservice to the console, just like the authorization rules. Over the years, the number of customer accounts grew dramatically, and with that, the request rate into our system grew as well. We developed more and more features and more microservices, which were exposed through our API gateway, and the API endpoint count grew as well. All this growth couldn't have been done without a decent employee growth. The more engineers we had, the harder it was to communicate. Best tips, which used to be passed as a word of mouth, were just not efficient anymore. We needed proper, easy, and understandable rules that all engineers could know and easily apply. As companies grow, small service problems become bigger problems. And as your company scales, your problems scale as well. And believe me, our problems scaled just so much. Slowly, our bouncer just started falling apart. Believe me, we tried doing all of what we could within our own team in order to save it. We enlarged the machines, we scaled upon more machines, and we added patch upon patch just in order for the bouncer to work. But soon enough, we had more problems and more issues we faced. Over time, our code got more complicated, and the code and the original goal of the service drifted farther away. We understood we needed a big change. We just didn't know what yet. Going back to our agenda, the first step in a successful migration is to identify the problem. There were many problems with our API gateway, and most were due to design decisions we made in early stages, which didn't take into account the big scale we would grow into. The main problem we faced was that the service was not scalable enough. The service and the proxy were designed synchronously, and the specific implementation we used in Clojure allowed up to around 60 concurrent requests per instance. Requests through our API gateway often download complex reports, and each request could take up to a few minutes to return. In order to solve this problem, we brought up a lot of redundant API gateway instances just to be available if needed. And sometimes, in times of peaks, our bouncer was unavailable. And let me just clarify here. Since the API gateway is the entry point to the system, if it is unavailable, the whole system would be unavailable as well. So availability for the service is crucial. A second problem we had was that the header size increased over time. And let me have a small recap. The bouncer, before sending the request on, before proxying it, would add user and account data to the header of the request in order for the receiving microservice to have initial data on the end user. Over time, we added more and more information to the account and to the header, and we just started working with accounts which had a big initial account data to begin with. HTTP header size is limited, as you know, and soon enough, requests of large accounts would just be dropped by the network. This forced us to make urgent and specific fixes per account. The last problem we had is that authorization was easy to break. The authorization relied on specific URL registration by the microservice. A small mistake by a registering microservice or even a human error could drop authorization for the receiving microservice or even for all microservices served by the API gateway. Now that we were aware of our problems, we needed to think of our main goals. There are many small goals and fixes we wanted over time, but here we focused on refining only to a few and simple goals which would answer our main issues. One, we wanted a scalable service, which could withstand peaks of traffic. Two, we wanted a simple service, both in terms of code and in terms of design. Since tens of teams are using the API gateway, we wanted simplicity in convention rather than configuration. We wanted a few rules set in stone that all engineers could know and easily apply. And finally, we wanted an observable service. Since API Gateway is the entry point and the exit point of all requests, it is just the ultimate place to have a broad look over the whole system. Now to investigate our possibilities. From our point of view, we had 3 options. The first one is to keep making patches in code. We tried it, I talked about it before, but since the bouncer code was so complex, each patch took a very long time, risked us with unexpected bugs, and only led to a value which diminished very fast. Our second option was to use an open source or an off-the-shelf solution. We looked deeply into Go's traffic, which is the icon on the right. It's a Go reverse proxy and a load balancer. And we looked into Kong, which is an API gateway written in Lua and running on Nginx. None of these options just fit our exact needs, and we understood we would have to write a decent amount of code on top of these solutions just to fit them to what we needed. Our third option was to rewrite the service from scratch. And you guessed it, we chose this option, but we just didn't know what technology to use. Our gut said Clojure, since it was our comfort zone, both infrastructure-wise and knowledge-wise. We knew there wouldn't be any surprises going in that option. But we also thought there might be a language more fitting than Clojure for this type of service, and we wanted to try something different. Step 3 in a successful migration is choosing the right technology. There is no perfect choice, and there are pros and cons to each. We examined a few aspects in order to reach the best technology for us. We researched the technology which could withstand our growing traffic. We minded the documentation and support each language had, both in having a supporting tech community and understanding if our infrastructure group would be able to support the language we would choose. We minded the learning curve in going to a language different than Clojure, but also wanted to take this opportunity to go out of our comfort zone and test if we, as AppsFlyer engineering, could grow and work with a second language at our company. And therefore, wanted to choose a language which could grow with our business and could be fit for a number of services at our company. As you probably know, Go has many advantages for this type of service. Go is scalable and concurrent by nature. It has a rich standard library, which includes a reverse proxy out of the box. It has good performance, and it has automatic memory management. In addition, it has a steep learning curve, and we could allow the time to properly learn it. In addition, this is the first service AppsFlyer will have in Go. It will be a true experiment to see how well we could introduce a second language, and it could have vast implications on all of our engineering teams. Our fourth step in a successful migration is correct design, which would answer the initial goals of our service. We wanted to keep this design simple and concise. Each HTTP request coming in would go through a complete and ordered pipeline of authentication, authorization, service discovery, and then would be proxied on to the designated microservice. We solved the increasing header size by passing only the user ID of the requesting service instead of all of the account data like before. Now let's look at the architecture. The new API gateway would have requests coming in from the web. Each request would then be authenticated by using information out of the same account repository as before. The bouncer would then authorize each request by using URL conventions, I will say in a later slide. And then the request would be proxied onto the relevant microservice, passing on only the user ID on the header and not all of the account's data. Then each microservice use a designated client in order to get all user and account information, like the bouncer used to add to the request. Now let's see how we answered our initial goals while using Go and just implementing a more correct design. Our first goal was to have a scalable service. One could withstand our growing traffic. Go is scalable by nature, and the feature that it supports out of the box that boosted our scalability the most is Go's built-in reverse proxy. Its biggest advantage is the ability to stream the data through the proxy instead of storing it in memory. Using Go's reverse proxy allowed us to handle roughly 100 times more concurrent requests per instance than our previous API gateway design. And I'll say it again because it's really crazy. Our bouncer used to handle around 60 concurrent requests per instance, and the API gateway, the new API gateway in Go, allowed us to handle 100 times more. Now let's view exactly how simple using Go's reverse proxy is. All you need to do is to import package HTTP util and just use 2 lines of code. In order to create the reverse proxy, you just need to call the new single host reverse proxy. And in order to serve the request, you need to call the serve HTTP function on the proxy. It's really that simple. You use these 2 lines of code, and you have a scalable and working proxy which streams the data through it. Our second goal for the service is simplicity. One way we tackled it is by using convention rather than configuration. We chose a few conventional query params, which would be authorized by default. Now let's view an example. A specific microservice designed a URL with the app ID query param. The app ID query param is conventional, and the value would be authorized by default. So the request coming in would first go through authentication and then onto authorization. Once the conventional query param is found, the value is passed to the authorization engine, which basically checks if the authenticated user has permission to view the app it is asking the data for. In case it does, the request would be proxied on to the relevant microservice, and in case it doesn't, the request would be answered with a 404 and would not be proxied on. We're still at our simplicity goal, and an additional way we tackled it, in my opinion, is using Go's statically typed language, statically typed nature. In a statically typed language, like Go, variable types are explicitly declared and enforced upon compilation. On the contrary, in a dynamically typed language, like Clojure, variable types don't matter, and you would find out about a type exception in runtime if you're lucky. In my opinion, moving to develop in a statically typed language helped us tremendously while creating this new service. It forced us to face critical questions and make a tight contract with ourselves and with others right when we first started writing our first lines of code. In addition, the type served as a great initial documentation for us. A large amount of errors were caught early in the development process, closer to the location they were introduced, making fixing them much simpler. Our third goal was to have an observable service. Since each request passes the API gateway upon entry and upon exit, the API gateway is the ultimate place to have metrics and to have a broad look over the whole system. We monitored many events happening inside our API gateway, but decided that for us to be able to monitor the system as a whole, we would have a metric on the rate and on the latency of each request going to each service. This was a true benefit for the whole company in order to understand customer trends, how each service withstands them, how each service compares to another, and how we're doing in terms of our initial SLAs to our customers. Now, we have a service. It's more scalable, more observable, more reliable, has conventions by default. It's really just amazing. But it has no services using it just yet. Until now, all developments and refinements were done in our own team, and we understood that we're now ready for a full company migration. As Jeffrey Garrett once said before me, everyone likes progress, but no one likes change. How do we convince all engineering teams to complete the migration? And how do we give them enough confidence the change is better? Or more important than that, how do we give them enough confidence the change is not going to cause a degradation? And finally, how do we bring up the urgency for such a change so that the migration would not be dragged for years going forward? The migration of the new API gateway demanded change over 80 API services, which were spread around 15 teams, 3 offices, and 2 countries. We wanted to have a controlled and gradual rollout in order to be able to detect, manage, and fix issues we saw along the way. For the controlled rollout to be successful, we needed both old and new flows running at the same time. We used AWS's ALB, which is an application load balancer, to route the traffic between the old flow and the new flow based on URLs. That really means that URLs of migrated services would be routed automatically to the API gateway, and URLs of unmigrated services would be defaultly routed to the bouncer. In addition, the new flow, the API gateway, used JWT token for authentication, while the old flow, the bouncer, used session cookies for authentication. In order for one authentication to be able to seamlessly travel between the 2 API gateways, we created both authentication flows in the 2 services. Now I'll just show a picture of what I talked about. This is the architecture we had for the whole migration. So to have a small recap, we had an ALB, which is right in the middle, which migrated the traffic between the API gateway to migrated services and automatically routed the traffic of unmigrated services to the bouncer. The bouncer used session cookies for authentication while the API gateway used JWT. But during the migration, we had the 2 authentication flows in the 2 services so that users could be served automatically by the 2 different API gateways without even noticing they're being served by 2 services. Like I said before, the challenge here was not code anymore. It was fully psychological. It was hard to convince the different engineering teams to touch something they didn't know much about and is currently functioning. Did you ever hear, if it ain't broke, then don't fix it? Well, that was the overall feeling when we just started the migration. We had to find a way to convince all engineering teams to actually take the time and migrate and to do it on time. We prepared a simple migration plan, which had a few steps in it. It was truly a manual for dummies, explaining step by step how to stop using the bouncer and how to move to the API gateway. It explained in detail the new conventions and the authorization rules. We made sure all teams knew about the migration benefits, how the service is more stable, more observable, and more straightforward and easy to work with, so that people would know they're putting the effort now, but it will be worth their time in the long run. We know that practice makes perfect, so we wanted to allow to test this intermediate step locally and in staging. So we created full support for this whole architecture locally, and we used an Nginx instead of the ALB, so that the teams could test all the implications of the migration and even test a rollback if they wanted to. In addition, we made sure all teams would have to perform minimum changes on their services, and we created a predefined client which would give all services the same response as the bouncer used to add to the request. One of the best things we've done, which eased this migration for all teams and helped tremendously while finishing this on time, is the code and the thought we put for this transition period. We're not afraid to write code that we knew would only last for a few months while we were in the step, and we looked at it as a bridge from an old and outdated technology to a new, better technology. We knew that if we would build a strong bridge, the teams would be convinced to actually walk and move on to the other side. Finally, a few long months after the migration, it finally happened. We finally worked only with the API gateway, and we shut down the bouncer and the ALB. The best thing is, which is kind of funny to think about, no end user noticed the change, and we received much more confidence over our whole system and much more observability as well. Now, a year and a half after the migration has been completed, we can look at the benefits. Thanks to Go, we have a much more stable system, and thanks to its scalable nature, we're now only using a few instances instead of tens that we had before. The simple pipeline design made it so easy to add more authentication methods and a throttling mechanism we added over time. The conventions, the authorization conventions, allowed us to put in more conventions and more conventional query params by a matter of a single deploy. And our experiment with inserting a different language other than Clojure has succeeded. And we now have 41 services written in Clojure, in Go, I mean, and more to come. So to wrap up, we met all of our goals while carefully following a few steps. We identified the problem, which was unsatisfying scalability, header size which increased over time, and authorization which was easy to break. We defined our goals which would answer our main issues, which was scalability, simplicity, and observability. We chose the right technology, and choosing Go has been proven to be such a good decision. Its steep learning curve made this fast, easy, and really fun to learn. And its standard library support of a reverse proxy made this a real measurable change and a more robust one as well. And most importantly, we now have another go-to language that we could choose when the fitting problem arose, which made us a much stronger engineering team. The fourth step was the design, which we made an effort to make it as simple as concise as possible. And finally, a well-executed migration, truly minding the people behind the screen, actually needing to make the change and migrate. Thank you very much. Any questions?
It's a very short question. I would like to know how do you measure the scalability? How do you testing it? Load testing, performance testing, and so on.
יעבוד לי פשוט? Okay. You mean in when we were developing or right now?
Right now.
Right now we measure the throughput and the latency while using metrics. We know the rate, like I said before, we know the rate and the latency of each request coming in, and we can know and we know how many instances we have. We look at the metrics we get, and then we know how our service is acting with it. Talk manager שלי.
How long did the whole process take?
The actual development took, I want to say, 8 months. Just the development itself. In the beginning, only one person was working on it, and then we added more people along the way. And the migration took around 4 months, until starting with the first service and until we had the last service move.
So the design was started along with development? I mean, what was the head start all in all? Once you thought of a project of a need until you finished the final migration?
The amount of time?
Yeah.
I think it was a year and a few months. A year and 2 months, something like that. It took a while. It was a big project.
Okay.
Okay, thank you.